the NAND gate is the one at the end of the last lecture because it was like a little bit tricky for me.
This one?
Yes, like I got until like you compared between like
I even used the Heisenberg rule on this.
right. So
I did it with I wrote logic equations first. Did that make sense? And then I did this truth table part.
okay.
What part didn't make sense? Truth table should be really straightforward, right? Did you follow this truth table?
Yeah.
So that's an AND gate. That's the truth table for an AND gate. We just looked at the switches and we tried all the combinations.
Yes. Sorry. Yeah.
The logic is a little trickier. The way I wrote this logic, I just said for down here, if you take the AND, the N channels, I said when two things are in series, that's an AND function, right?
Okay. So this is exactly how we actually build as a logic, or we will use this CMOS.
This is CMOS. There was N channels here, right? These are N channels, and these two are P channels. That's CMOS.
Yeah, but not inverters. Like we are not using it in the inverter.
Well, we need more than inverters. We need to build more complex circuits. We did inverters. Now we're doing a NAND gate. Then we're going to do a NOR gate. And once you can build an inverter, a NAND, and a NOR, you can build anything.
Okay. So that makes sense. Okay.
Okay.
And we're not doing AND or OR gates because.
Well, I'm going to talk about that in a second.
Okay, fantastic.
Yep. Okay.
I just
Well, I
have
guess.
one question. Sorry, if that's okay.
Yeah.
Is it like for PMOSs, would that be basically an A bar and a B bar, like when you put them into a PMOS?
Yeah, like for up here, when I wrote the equation for the PMOS, I said Z equals A bar or B bar.
Okay, but the bar is because it's from a PMOS gate. So
no, the bar is because to turn this gate on, you need a 0 here. So the 0 turns it on.
Okay, that makes sense. Yeah.
And they're in parallel. That's why you get an OR. That make sense?
Yeah, that makes sense. I was just wondering where the bar came from.
Yep.
How about the barrel NMOS?
The bar over NMOS like that? That because these are added together when A and B are together, that the output goes low, not high. So that's where this bar comes, because this pulls the output low.
Yeah, but I mean, if we put the NMOS in parallel,
then it would be A or B bar. And we're going to do that in a second.
Okay.
When we make an OR gate, that's how we're going to do an OR gate. Okay?
Okay, makes sense.
Okay. So yeah, we're still in week 2. We're going to keep talking about CMOS logic gates today. We may finish it on time. I don't know. We'll see. Maybe not. So we're going to go back to here. So this is what we did last part of last day. We built this NAND gate, and I analyzed the logic for the NAND gate, and I did this truth table, and this is our symbol for our NAND gate. And somebody said, "Oh, what about AND and OR?" Well, to make an AND gate, you just take a NAND and an inverter, and that makes an AND gate. Right? Now, obviously, a NAND gate is better than an AND gate, right? Because this NAND gate this AND has 4, and the inverter has 2 transistors. So this has 6. So if you use an AND gate instead of an AND gate, you have more transistors, more power consumption, more area. So we like to use NAND gates in CMOS as much as we can. But normally we don't have to worry about that. We're going to see later on we have a synthesizer, and it'll optimize this for us all the time. Okay, so where am I at here? Let's just go down here a little bit. Let's go here. So now we're going to do the opposite. Instead of 2 series ends, we're going to put 2 parallel ends like this. And we're going to call that Z. I'm going to call that A. I'm going to call that B. And now if I were to write the logic equation for this, it'll be when things are in parallel, that's an OR function. Either or of them will make a connection, right? And again, the same thing. When they go, when A or B is high, the output will go low, so we get a bar here. So Z equals A or B bar. And that is a NOR. And we always said, well, the P should be the opposite of the N. So these are in parallel. We want two series P's like this. And if we were to write the equation for the P's, it would be A bar and B bar, right? So if A is low and B is low, we make a connection path and the output goes high. And if we De Morganize that, we invert the inputs and the outputs and change the sign, and we get A or B bar. And guess what? These two things are equal, which is what we like. So this is a CMOS NOR gate. And if we do the truth table, using our Heisenberg principle. So A and B are 0. So that means this switch is closed, this PMOS switch is closed, and both these switches are open in the bottom, right? And when both the P's are closed, it will pull the output high, so we'll get a 1 here. And any other combination will have one of these P's open and one of these ends closed, or both of them, which means we won't have any path to the VDD, but we'll have a path to ground. So these are all zeros. And that's the truth table for a NOR gate. And we go back here. This is our NOR gate. We just built. There's the logic function for it. There's the truth table, and there's the symbol for it. And if we want an OR gate, we take a NOR and an inverter, and we get an OR. And this has 6 transistors. This has 4. This has 2. NOR gate is much better than OR gate. Fewer transistors, lower power, smaller area. And now we have inverters, NANDs, and NORs, and we can build anything. We're unstoppable now. The sky's the limit.
So we typically design with an OR, and then we convert to NAND and NOR, right?
Yeah, we would prefer to use NAND and NOR circuits. In CMOS, NANDs and NORs are the best. But we will see later, we very seldom have to use these gates ourselves. I make the analogy, do you ever do any assembly programming?
Yeah.
So like an assembly program, you do these like, you do like jump here, go here, add these 2 numbers or whatever. You only do that in very special cases, because normally you write like Python or C or something, and it generates all that low-level assembly code. Well, using these gates like this is like writing assembly code when we have to actually design at this level. We do have to do it sometimes, but very special cases when we're looking after super efficiency. Most of the time, we're going to use what's called a synthesizer, and it's going to generate the logic for us automatically.
Okay.
Yeah, SISC-3's the 1006 was a bit of it, yeah. Well, if you've ever written assembly code, you know you don't like to do it very much, right? It's kind of painful, right? Much easier to write a high-level code. But it's important to understand this, because remember we said we're going to start from the bottom and work our way up. So we want to know how things that work at the lowest level, because when there's problems with delays and power and something, we have to know how these things are working. Okay, so that's the gates. Oh, I didn't realize this was here. Okay, I'm gonna do 2 more slides. It turns out that, well, let's go draw a picture. Let's draw a picture here. Picture. Let's make a circuit here. I'm gonna make an and. I'm gonna make an or,
Just wait.
and I'm gonna make an and. Okay, I just arbitrarily picked this, and I'm gonna have inputs A, B, C, and D. I'm gonna call this output. I don't know, Z. Now, from what we've just learned, how many transistors? Somebody's got to mute you. Muting you. You can unmute yourself, but somebody's making a lot of noise there. So we just learned how many transistors in this AND gate?
6.
There's 6, right? And this OR gate has 6. And this NAND gate has 4. So we took 12 and 4 is, this would take 16 transistors. Now I'm going to make a little circuit here, and this is called the complex CMOS gate. And I'm going to do this AND. We know an AND is 2 transistors in series. Okay. So I'm going to call, first I'll do this top one. I'm going to have an A and a B. They're in series. And for this bottom one, which is OR, I know OR is 2 things in parallel. So this is going to be a C and a D. And then these 2 things are ANDed together, which is in series. Actually, you know what? I'm just gonna move these up. I'm gonna put this. These were in parallel. C and D. And now this AND means in series, so I'm going to put that in series with that. And I'm going to write this Z. And so if I wrote the logic function of this, it would be A and B. And that is AND it with C or D. And that's what this gives us AND. And then there's a bar because the whole thing goes low. And so this circuit has the same functionality as that circuit. That's the N channels. And if I were to draw the P channels, can I move this out of the way? How do I do this? I need to select it. Oh, I don't know how to select it. Oh, maybe I do. I don't know. Oh, not like that. Oh no. Okay. How do I move this thing? Move. Can I move it like that? Oh, I don't know. Move it with my mouse. Must be an easier way. Slow. Okay, go over there. Okay. We already learned to make the P's, we just want the opposite connection. So this A and B were in series, so we're going to make them in parallel. So that's A and B, they're in parallel. And then C and D are in series. And then these 2 groups are in parallel. Yeah. So that's the opposite. So this whole circuit with these P's and N's does the exact same as this circuit. And this is called a complex gate. We can kind of merge a bunch of gates together. And the big advantage here is we have 1, 2, 3, 4, 5, 6, 7. This only has 8 transistors, so half the number of transistors. And when I have half the number of transistors, that means I have it's faster, it's lower power, less area, less cost. So it's way better. This is called a complex CMOS gate. And yeah, so complex CMOS gates, conventional topology, you just sort of, you have a symmetric response by equalizing, pull up, down. Well, anyway, you make this duality, you make the NMOS and PMOS. This is another example. The C and B are in parallel and the A is in series with that. So I make C and B in series and parallel with the A. You get the idea. Anyway, these are used wherever possible to kind of improve the performance of our CMOS circuits. That's called a complex logic gate. Any questions about that?
Sorry, Sarah, please, could you go back to the drawing?
Yep. Hey, we could do the demorganize this here. Let's write the equation for this part. This would be A bar or B bar, right? And then that's ORed with C bar and D bar, and the output goes high. So let's demorganize this. How we get A bar or B bar, and that gets barred and with C bar and D bar, right? And then if I demorganize these little individual things, I invert the inputs and outputs and change. So this would become A and B, and all the inversions disappear. And this becomes C or D. Oh, that was a D, not a B. And then I put a bar over the whole thing.
Professor.
Oh, sorry. What did I do here? No, I still had that was still an OR there. Then I ended. Yeah. Yeah, you got a question? And those are equal. No, what did I do wrong? Oh, you know what? Let me hold on a sec. Just let's do this again. Let's do this again.
Hi, Professor.
Yeah.
I was just wondering, so do you do only the demorganizer from, like you just use the normal method of getting the Boolean equation from the NMOS side, and then you demorganize it on the PMOS side?
1 second, I'll answer that. So this was A and B, invert the inputs and the outputs, or C or D, with the outputs, right? And then this goes to A and B, and it was C or D, and invert the inputs and the outputs. Those are equal. What I normally do is I just like to do the N channels, and then the P channels are easy. You just have to use the opposite configuration. So if these, like I didn't write this equation, I just wrote this equation down here. I don't even need this equation to draw the circuit, but this is a good way to check. If you want to double check that you got it right, you can write the equation for it. So this was like a double check, right?
So sorry, Professor.
Okay, thanks.
So if we design this logic gate, why did not we satisfy by the bottom part of the circuit? Like why we did not only use
We did. The bottom part of it satisfied the circuit, this equation, but the bottom part can only pass good zeros, right? N's only are good at zeros.
Oh,
We
okay,
need the P's to do the positive ones.
got you.
So before we even get there, given the logic that you first started with, can we just use the transformations to simplify the logic, and then that will actually give us the same result? Like if we push through the whole of the NAND, we get an OR with two inverted inputs, and that will give us an OR and an AND at the inputs.
Here, you want to simplify this first. Is that what you want to do?
Yes, because I mean, you gave us that, but then like,
Well, let's try to simplify this. What do you want to do?
so we push through the NAND and we convert it into an OR with two inverted inputs.
An OR with two inverted inputs, yeah, like that.
So that makes for an AND and an OR. When
So yeah, you can go like that. And then
Okay.
that, you can just bring the bubble back here. So that
Yes.
is there and there.
so that is exactly what you have right now there.
Yeah, this is the exact same logic function, but if I were to build this out of these basic gates, I would still have the problem. I have 4 here, I'd have 4 here, and I'd have 6. So I've helped a little bit. Now I've got 14 instead of 16. But here I've only got 8.
But since you have an OR at the end, wouldn't that okay, no, sorry, I was confused there.
So you made it a little bit better here, yeah, but not anywhere close to what I did.
Okay.
That makes sense?
Yes.
Because if you were to implement this the way you want to do it, like you'd have to have like a NOR, then you'd have another NOR, 2 input NORs, right? And then you would take the output of those and you would feed them into a NAND. Sorry, oh, we had NAND. Sorry. Your version would look like this.
Yeah, I got confused because I thought that by leaving an OR at the end, it will simplify even further, but I realize it's not equivalent.
You made an equivalent circuit, which is a little bit. Your circuit would look like this, and then you would go into a NOR, which would look like an OR, which would look like a NOR. These are P's. And then you'd have an inverter. Oh, I didn't draw all the details, but you got what I'm saying, right? So you needed this 4, 4, 4, and 2, which gave you 14. Yeah, so this is better. This is a different thing. A complex gate is different than these individual basic gates. Like we kind of call these the basic gates, the NANDs, the NORs, the ANDs, and the ORs. This is a complex gate. Okay.
Yeah, that makes sense.
Okay. Next thing we're going to do this slide, then we're going to have some bonus questions. So